Hello everybody, and welcome back, and welcome to week 3 of this VEX course. And this week we're going to be diving into much more advanced VEX than we've been doing up till now. So I hope everybody's following up to this point. By this stage you should be able to write simple expressions in VEX. You should be familiar with the syntax, how to read the help file and figure out what arguments you need, and just structure basic code. Okay. So this week, we're now going to start diving into some really cool things and trying to understand how VEX is working, under the hood, so to speak. So we're gonna really dive into the nitty-gritty of how it works, what it's doing for you, and then how to use that to get amazing results. So I've prepared a few kind of advanced examples here just to discuss a few aspects of how VEX is working, so that after this point we can move into deeper, much more complicated expressions. Okay, so one thing that we need to understand about VEX before we continue is what it means to run over. So all our wrangles are asking us what type or class of geometry we are going to run over. If we run over detail, which is the whole geometry object, it'll execute only once. Or if we run over primitives or points or vertices, or then numbers is not running over particular geometry, but it's running a set number of times. Now, ultimately what this kind of boils down to is it's a loop, right? It's very similar to other loops that we will be using in VEX, except for two things. One is that it binds all the data out simultaneously at the end of the loop, not on each iteration of the loop. So essentially what it does is it's storing the result of the loop in memory, and then when it's done executing it all, it writes all of that data out for us. Now you'll understand why that's important just now. I'm going to give you an example and show you why we have to know this. And then the second difference is that we cannot exit that loop early. Okay, you can return from the loop at a particular point in the script, okay, like exiting from a block within a loop, but it will continue to loop over all the rest of the points or primitives or whatever class we've chosen to run over. It will go to the next loop. So essentially returning is actually like continuing. If you know anything about coding, you'll know what continue is. And in this case, a return almost acts like a continue because it cannot just run over only 50 of your points and then stop. It has to run over the rest. Okay, so those are the only two major differences between running over versus an actual loop. But essentially it is a loop, and that's important to keep in mind. Okay, so when we say run over points, it means that every bit of this code is going to execute on point number 0. Then the whole code is going to execute on point number 1, and so on. And VEX is really light, so generally this tends to be fine. But if you have millions and millions of points, and you're running over your points, it may start to get a little heavier. Particularly depending on what's happening in the script. A simple setting of data or getting something or running one basic expression is going to be fine, but if you've got lines and lines and lines of very complicated code, maybe something that's doing proximity checks or ray casting, something that is memory intensive, and then you have a million points or millions of points, then it's going to be heavy. Okay, so just keep that in mind. Right, so I'm going to walk you through what this example is doing, and then I'm using this as a very simple proof of a certain set of things that are happening in VEX. So first thing I'm doing in here, this line, I'm basically setting a value called getFoo, so a float called getFoo, and I'm setting it from a detail attribute. So I'm reading a detail attribute on myself called foo. So basically it's going to this section here under the detail, looking at foo, grabbing that value and setting it as the getFoo value. Okay, and I'm doing that first. Second thing that I'm doing is I'm going and setting a detail attribute. So even though I'm running over points, I can use this expression to write data to a detail attribute. Okay, and I'm writing the foo attribute and I'm setting it, so I'm overwriting what it is with my current point number. So when we're running over point number 5, we're going to go to foo and set foo to equal 5. Now it's important to note that I'm getting the value before setting it. So essentially I should be reading what it was on the previous loop, the previous iteration. Okay, so when we're on point 5, ideally get foo should now be equal to 4, because it should actually have gone and fetched the foo value, which would have been equal to 4. Then it's going to set foo to equal 5. And then when we move to point 6, it'll go and grab the value 5 and then go and set it, overwrite with a new value of 6. Okay, now that's what should be happening here if it was a normal loop, but it's not. Okay, what you'll see here is that get foo is equal to 0 all the way. Okay, every single point is getting a get foo value of 0, but our detail attribute is set to 99. And this is proof of what I said earlier, which is that it runs over all the points, storing all the data in memory first, and then binds it out. Okay, so let's ignore this first line for a second and let me explain what's happening. This line over here is executing. So we get to frame point 5 again. On 5, it's setting the detail attribute of foo to be equal to 5. Okay, it doesn't matter what it was before, it just says make foo equal to 5, and then it says make foo equal to 6 and make foo equal to 7, and it keeps going all the way up until the end. So the last command that was executed on foo is saying foo should equal 99, because we have 100 points which are numbered from 0 to 99. Okay, but the foo value hasn't actually changed yet. It's just got a bunch of commands that are telling it to be equal to a different value. So even though foo is still equal to 0, in memory it's saying that foo is equal to 99. And it's important to note that, because when we try to run on every single loop and set the get foo value to be equal to whatever the current value of foo was, it's fetching a value of 0 because it's still 0. That the data has not been bound out to foo yet. So every time we fetch it, it's still 0, because only at the end of running through all 100 points does it actually set the value of foo to be equal to 99. Alright, so there's proof of exactly that, and this will come in handy later, because sometimes you need to run multiple wrangle nodes. You can't just condense everything into one giant script. You actually sometimes have to run a wrangle and immediately after it run a different wrangle that's setting a few other attributes, because if you need to access data that you're setting on other classes or other neighboring points simultaneously, then you need to set all that data first, and then in a separate wrangle you can access that data, because after the wrangle it will bind out, and then the next wrangle in the sequence can read in that data. Okay, so I'm going to talk you through an example of that just now as well, so you'll see. But anyway, that's what that section proves. Now we move on to here. So I've got an if statement, and I'm just checking if my point number is greater than 50. If it is, I'm returning. Okay, so return is, we're going to talk more about this later when we do talk about blocks, but just for now, just know that it's checking this condition, and if it's true, then it does this line of code. And the line of code is saying return, which we will also talk about what returning is later, but essentially it's exiting the loop. What this is saying is don't do the rest. Just stop here and leave. Okay, but it doesn't just quit after 50 points and then therefore only run 50 times. It does continue to each point. So then when it comes back to the next, so point 51, it will run through, it'll do these first 2 lines and then hit this point and then exit. And when it hits point 52, it's going to again run these first 2 lines, hit this point and exit. right? And the proof of that is the fact that if it was just exiting off after point 50 and never re-entering the loop, then our foo attribute would also stop at 50. But we can see that it gets to 99, okay? And yet our test attribute, which I'm setting here to just be equal to 1, so on every point, on point 0, it says it's equal to 1, on point 1, it's equal to 1, it just says 1, 1, 1 all the way down, until it hits 51, which is greater than 50. Therefore, it hits this return, exits, and does not set test to be equal to 1. And because we haven't initialized this before, it's a standard float, so by default it will assume that if it has no value, then it's equal to 0. Okay, so it's defaulting to 0. Okay, which is kind of bad practice. If you wanted to do this, you should actually initialize your attribute first. So a little bit of bad practice, but this is just to prove that it doesn't continue to run this line. It stops here, but it stops here and goes to the next iteration in the loop, which is not what return is normally supposed to do. When you return, it normally actually just stops the entire loop at that point and exits. Okay, but it does not exit the entire wrangle. It will continue to the next iteration, right? And this is a difference between loops and wrangles running over. Okay, so this sort of just shows exactly what I've said before, which is that data is stored in memory first and only bound out at the end, which is one thing. That returning does not actually fully exit the loop, that it actually just continues to the next one. Those are the two things I wanted to prove with this example. Okay. So now we know why sometimes we need multiple wrangles in a row. And I'm going to show you an actual practical example of that. So let's move on to the second example. Now, all I have here is a sphere. Okay. I'm remeshing it just to get a bit more complex geometry, and I'm running a mountain SOP just to give it a little bit more, you know, that it's not so uniform. Okay, so we want some divots and some, you know, like bits sticking out. Okay, because what I'm going to do is I'm going to calculate a tangent on all of these points, right? And then I want to measure the difference in angle between each point's tangent and all of its neighboring points' tangents, figuring out which one of those points has the maximum difference in angle, okay, and setting that value as almost like a curvature value. So it's a float value that's essentially saying in areas where there's a huge difference, so maybe a very sharp divot where it dips in, it'll have a very high curvature value, whereas an area that's quite flat will have a very low curvature value. Okay, so that's my goal. Now here I have two wrangles where I'm doing exactly that, and here I have one wrangle where I'm doing exactly that. And these two wrangles have the combined code of everything that's happening in this one wrangle. Okay, so these top few lines is exactly the same as this first wrangle, and then the bottom few lines is exactly the same as the second wrangle. So there's nothing different happening between these two except the fact that I'm running it in two separate wrangles. And what we'll see in here is that this one does work. Okay, hang on now, we can't see, for some reason this is not writing out the tangent. This is very interesting. Okay, let me just copy this code in. Okay, that's in fact, you know what I think has happened here? I think sometimes when you hit undo, I've known on a lot of wrangles, when you hit undo, sometimes it clears the code, or it'll clear you've done a lot of changes, but it will undo right back to the beginning. So when I copied this wrangle and changed the code, it must have undone it so that these two are identical. Anyway, so you can actually see that I have directly copied this entire bottom chunk of code into this second wrangle. Okay. Now what you'll see here is this is exactly the result I wanted. So I have, oh, in fact, sorry, we can see highlights here, by the way, as I rotate. So all I'm going to do is actually right click on here and turn off specular, so we don't see any highlights, so it doesn't get confusing when we're looking at our actual grayscale values. Now what you'll see is that the areas that are brighter, closer to white, have a much higher curvature, and then the areas where it's black have low curvature. And when I say curvature, I mean just in comparison to its neighboring points. Okay, so this kind of flat plane area here, the center of it will be black because all of these have a very similar tangent, whereas at a peak it's going to have a much higher value because all of its neighbors have much more different tangents. Okay, right, so let me show you how I'm calculating this quick. If you ever need this technique, you can use this, but I am actually, we'll go through examples like this later. This is more to show you an example of how the two angles works, but if you want, you can copy this code and on how to calculate tangents and things like that. Okay, so all I'm doing is I'm creating a vector up with just a default sort of 0, 1, 0. So I'm just giving it an up vector. And then I'm also storing my normals in a vector called norm, just because I don't want to overwrite normals constantly. I just want to work with norm, and then at the end I can write it if I want to. Then I'm creating another vector which I'm storing as underscore tangent. I normally do this when I have temporary values. So when I know that this tangent is not being calculated 100% correctly, I want to work on this value and then later store it in an actual tangent. Then I'll use it like this. Okay. So it's like a temp value. And all I'm doing is running a cross product on the normalized vector and the normalized up. Okay. I'm not going to go into this. We'll maybe talk about this later when we're doing actual vector things in the complex example we're going to do in I think week 6 and 7. But anyway, so I'm cross producting between two normalized vectors. Then I'm taking the result of that into another normalized vector and normalizing the normal again to calculate a new version of the up. So I'm overriding up with an accurate up that has been cross-producted. And then on the final step is to calculate the actual tangent using the cross product of the normalized normal and the normalized up vector, which we fixed here. Okay. The result of which is that we get these tangents, okay, which are running clockwise around our sphere, okay, with up with y as an up vector. Okay, so that's what we should be getting, and we'll get that on this result too. But what we will not get is the correctly stored foo values, okay, and the color values. So essentially this max angle, okay. So let me talk you through this next second section of the script, right? All I'm doing is here, I'm creating a neighbors array. So it's just a collection per point of neighboring points, right? We'll talk about arrays actually in the next lesson, so you'll start to understand what I'm doing here, but this is just an example, okay? So I'm running a neighbors function and storing all the neighbors in an array. Then I'm initializing a max angle of 0, because I'm going to be adding to this. And then I'm running, so I'm doing a for loop. I'm running over all of my neighbors. So I'm I'm fetching the tangent, and then I'm calculating some dot products and lengths of the two, right, in order to calculate the angle. Now this, let me just show you, this has gotten a little bit complicated, but all I'm doing is, this is just a normal maths expression of how you calculate the angle between two vectors. Okay, so we need the arc cos, so the arc cosine of the dot product of the two vectors. Okay, so that's dot. I'm trying to write with a mouse here, so it's really shoddy. And then the so the product of the two lengths of the vectors as well, and then we divide them and run that through an arc cos to get the angle theta. Okay, so that's all I'm doing. I mean, I literally Googled that. You don't have to, know your maths or you can literally Google it and find this. Okay, and I'm just running that here to calculate the angle. And then I'm taking the maximum of that angle and then our stored, which is 0. So obviously the first time it will store that value, but then each time it loops over, it's going to, if the new max angle is, if the new angle is higher than the old max angle, it will choose angle and store that as the new max angle. So by the time we're done with the loop, essentially what we've done is calculated the highest angle between each point and its neighbors. Okay? And then I'm just writing that max angle out as a foo attribute just so we can visualize it, so I can show you what the values are coming out as. And then I'm also storing it in color, but I'm fitting it. So between 0 and 180, because it's in degrees, I'm giving it a 0 to 1. Okay, so we should be able to see that color. But in this example where we have only one attribute wrangle with the exact same code, the tangents work, because the tangents are being set up here, and these do not rely on the values of neighboring points. Okay, these only rely on the values of itself, right? We have a constant value here, we have the normal of ourself, and we are just using those values to calculate new values and setting a new value. Nothing here relies on a neighbor, which is why the first half of this code works. The second half, though, we're running this neighbors function, and when we go to each neighbor, we're fetching the value of the tangent, okay? But this tangent is only being set here. And this shows this value is going to come back as 0 on all of these points because this is still being held in memory. This has not been actually calculated and stored on each of the neighboring points. It has been calculated, but it's stored in memory, not on the point. So when I go and fetch the value of it, it's still going to return 0 until the end of this wrangle. When it exits this wrangle, it's going to go and write these values to the points. And therefore, I'll be able to, after that point, get the tangent. So the result here is we still get the actual tangent, but then when we calculate the max angle, every single time it's comparing the dot product between our current tangent, which we have calculated, and then the tangent of our neighbor, which is 0. So the max angle that's going to come out of there is exactly 90. And it will be 90 on every single one of these points. Okay, so you can see here it's 90 on everything, which is why it comes out as a constant color, because I'm fitting that between 0 and 180. So what we're getting here is 50% gray. Okay. Exact same code, no difference, just 2 wrangles at the correct place, and it works. And I want you to understand this, really thoroughly understand this, because you're sometimes going to be wondering, why can I not access that value? Just remember, you have to understand how it's writing the data out, when it writes out, when it binds. Otherwise, you will not be able to accurately create these loops and accessing data from other points or the same geometry but another class, like reaching up into primitives or detail or down into your vertices. You cannot do that all within one wrangle. Okay, so I hope that example helps. Now, in order to help you remember it, I just want you to think of it this way. Imagine you and 2 of your friends go to the shops, right? And you're going to go and try on a bunch of, jeans and t-shirts, okay? So you're trying on some clothes, right? And you take a bunch of clothes that you're going to go try on, and your friends and you all go into the change room at the same time, okay? So you each go into a separate booth. Now, you know what your friends were wearing before they entered the change room. You know what you were wearing before you entered the changing room. You also, when you try on the new pair of jeans, try on the new t-shirt, you can look in the mirror and see how you look with the new clothes on. Okay? You can even try the one t-shirt on, try the next t-shirt on. You're gathering data based on your current situation, okay? And you can change it and reassess yourself. But you only know what your friends were wearing before they entered. You do not know what they look like in the new t-shirt. Maybe all 3 of you took the same t-shirt, but it may fit you and is too big for your one friend and too small for the other friend. But you have no way of knowing that until you all exit the changing room. Okay? When you exit, the data is bound out. Now you, 1 point, can be aware of the current state of another neighboring point, your two friends, and can then make another decision on whether, okay, maybe the t-shirt fits your one friend better than you, and maybe you should go a size up or a size down or something like that. But you can only analyze that when you exit the changing room. Now that is, when you're in the changing room, you're in a wrangle. Okay? You're aware of yourself as you change, and you're aware of your neighbors, but only as the state before they entered. Okay? When you exit and reassess, you can enter the changing room again and now make new decisions, but that's a new wrangle. Okay? Every time you exit and enter that changing room, it's a new wrangle. Okay? So it all comes down to knowing if you're wanting to access neighboring points or other data that is being set, it only is set when you leave. Okay. I hope that analogy helps you. Like sometimes just little stories or things like that help me like remember how these things work, because it can get really confusing, like when you're writing all these crazy loops and things like that, and then you also start wondering why am I not grabbing the right value? You swear you're setting it correctly, you're fetching it correctly, and then you check that the values afterwards. Like in here, you could go and look at the tangent values and you're like, okay, but hang on, my tangent values are different, so why are my maximum angles coming out the same? My foo is 90 on every single one, but my tangents are different. Why? And stories like that help me remember, so I hope it helps you. Okay. Now, there's one more thing I want to talk about when it comes to advanced, understanding of wrangles and vex, is that the first input is special. Okay? Your second and third and fourth other inputs are reference inputs. In fact, you can even see if I hover over, it'll say geometry to process with the wrangle. And then on the second, third, and fourth inputs, it says ancillary input. Okay? So it's important to understand that the geometry that enters number one is the one that's going to be run over. It is the one that is going to be processed. Okay? Even if you don't change anything on that geometry. But if you have 10 points when you enter the wrangle and you run over points, what it means is that you're going to run 10 times. There will be 10 iterations of that loop. Okay? Even if inside that wrangle you're not changing those 10 points at all, but on each point what you're doing is going and finding a neighboring piece of geometry and finding a matching value and then setting the value on that piece of geometry, not yourself. Something weird like that. But what matters the most is that the geometry coming in determines the number of loops and what you're going to run over. Okay? And I wanted to put this a little example together just as a way of showing you that sometimes we're going to use kind of a strange looking technique here where you actually have nothing plugged in to your first input. And then you've got reference inputs in your second, third, and maybe even fourth inputs. This I often use when creating new geometry. Okay? Because if you want to run, let's say we want to create a duplicate of the sphere, so I want to run over 2,402 times. But if you put this into the first input, sure, we're going to loop that many times, but we also, those 2,402 points are going to come out of this output, as well as the new geometry that I've created. So now I've got double the amount of points that I want. Instead, I want to go and create maybe a duplicate of the sphere, except all the points are in entirely different positions. I just want to reference those 2,402 points, okay? But then do other things to create the geometry. So often I'll use this technique where I set my run over to detail. So I'm actually only going to loop over once because we have no primitives, points, vertices on this first one, okay? We could also set numbers and set it to run over once, but you know, it's the same thing, okay? But what I'm going to do is then inside of a for loop, I'm gonna set the number of loops manually. I'm going to use whatever I want to do. So for example, in this case, what I'm trying to do with this is create a point at every one of the points on my sphere. So I just have a sphere and I'm going to each point and creating a point in that exact same location, but only if it falls within the bounding box of this cube. Okay, so here's the result. Right, so that's doing exactly that. And if I move my box, then you'll see our points are created differently. Okay, so what I'm doing is I'm running a for loop. Now, like again, I said earlier, we are going to be covering loops later, so don't get too bogged down with exactly what I'm doing here. This is just to teach you how Vex is thinking first. Okay, so anyway, I'm telling it to loop equal to the number of points in input 1. So I'm saying loop 2,402 times. So now we're getting those 2,402 loops, but we're not having to get rid of geometry that's coming in. We have no geometry, so no geometry will come out other than what I create inside the loop. And then I'm just going and grabbing the position of those points, creating a bounding box value from the relative point bounding box value. Okay, processing using number 2 input. So we're checking our bounding box, sorry, our box which we're using for bounds. And then I'm only creating the point if our bounding box value over here, so our relative bounding box value, is equal to a clamped version between 0 and 1, which is a kind of a long, like, weird way of saying, is it inside the box? Okay, so only if the point that it's wanting to create at this position is inside the box, then it will actually create the point. Right, and that's what we get at the end here. Right, so this is just a strange little technique, but we are going to use it a lot later, so I wanted to point it out now that how important your first input is and how it can also sometimes be empty. Right, this is not a mistake. This is deliberate. Okay, so I hope you guys have followed and have understood. I've said this before. If this starts getting too complicated for you, please go back and redo week 1 and 2 until you understand, or you may even have to do additional research because we are diving into some complex things now, and it's going to be quite fast. So try to make sure you're keeping up. Okay, these are some basic techniques just on how Vex actually works and thinks. Because after this, when we start processing like much more complicated expressions, I want you to be able to understand the logic of why we're doing it the way we do. Okay, so I look forward to seeing you guys in the next lesson where we're going to be talking about arrays. See you there.